Okay, for this video, I'll be going through light thin converging lens tutorial. Okay, so question 1. The diagram below shows an object, which is this. Okay, an object that is placed in front of a converging lens. So this is a converging lens, right? The points marked F are the focal points. So these are the focal point. Okay, draw two rays from the top of the object in order to locate the position of the image. So there are actually three light rays that we can draw. The first one is the light ray actually passes through the optical center without bending. The second light ray that we can draw in this case is the light ray is parallel to the principal axis, and once it crosses the lens, it will cut the focal point on the other side. Okay, now you see that these two light rays, they actually do not converge. Okay, and these two light rays will actually enter the human eye. Let's say I have a human eye here, and the human will be thinking, the light rays must converge because they must come from a point. So the light rays that is drawn backwards is actually virtual. Okay, so this is for light ray 1 and this is for light ray 2, and they are drawn using dotted lines because they are actually not there. It is what the human perceive the light ray to come from. And in this position where they meet, okay, is where the virtual image is formed. That's why again we use dotted lines to show that all these are not real light rays. Remember when I told you, so in O level, if let's say this is the lens, right, and if by convention the object is always on the left hand side, okay, in O level, by convention the object is always on the left hand side, and if the image is found on the other side, and if this is the image is found on the opposite side of the lens, it will always be inverted and real. Okay, I and R, inverted and real. However, in this case, for this question, if the image is found on the same side, if the image is found on the same side as the object, right, on the left hand side, it will always be upright and virtual. So you can think of it as UV if it's on the same side, upright virtual. If it's on the opposite side from the object, it will always be inverted and real. Okay, so this is how you draw the light rays. So more important is you must know how to draw light ray number 1 and light ray number 2. So we are done with A. Now state the nature of the image. So since the image is found on the same side, right, on the same side, it is upright. Yes, because we started drawing from the tip of this object. So the tip of the image is also here and they are facing the same direction. That's why it is upright. Okay, and if it's upright, then it must be virtual. And lastly will be the size. You can see that the image size is larger than the object size, therefore it's magnified. If it's smaller, then we call it diminished. Okay, so it's either upright virtual or inverted real plus the size plus the size. The size you will have to draw out, then you will know. So what's one practical use of the folding arrangement is a magnifying glass. And how would you vary the distance between the object and lens to make the image look bigger? So if you want it to look bigger, okay, if I were to shift it, because the answer here says increase the distance between the object and the lens, but keep the distance to be less than focal length. Okay, I'll explain the first part first. I can actually use a drawing to show that. Okay, but maybe I'll erase this part. Okay, I'll erase all this. So the question says I want the image to be larger. So I can actually try out what happens if I increase the object distance from the lens. That means I can actually reuse this light ray here, right? I can reuse this light ray. But if I were to draw the one that passes through the center, okay, you'll see that they will actually converge at a further place. Right? So the image is actually going to be larger if I increase the distance of the object from the lens. However, you need to make sure that for the second part, you write this down. Keep the distance to be less than focal length, because once you have the object greater than focal length, the image will be on the other side and you wouldn't get the same upright and virtual image as what the question wants. Now, determine the linear magnification produced by this arrangement. Take note that this is no longer in syllabus, but actually I've seen some questions whereby they can actually guide you on how to find this. So that's why this question still stays in our tutorial. Okay, so the linear magnification is actually you can measure the height of your image over the height of original. Height of image over height of object. Or you can also measure the distance of the image away from the lens over the distance of the object. So it's always image over object. So it can either be height or distance. Height or distance. And over here it says similar triangles. You can try it out. Now for question 2, the following shows a full-scale diagram of a thin converging lens. So in our syllabus, mostly they will focus on thin converging lens. Okay, but they changed the sequence a bit. Now it is used to project a sharp image. That means this image is focus, right? It's in focus and it is on a screen S. So if it's on a screen S, that means it can be captured on a screen. And if it's captured on a screen, that means it is real. And if it's real, then it must be on this side. Must be on the opposite side as the object. Okay, we discussed this in question 1, right? So it must be on the opposite side. So we have the screen over here. This is the screen. So they want us to complete the ray diagram. So the first one that we can draw is ray number 1, my favorite, which is it passes through the optical center without bending. So make sure you know this, okay, and add in your arrows. The second one is you draw a light ray that is parallel to the principal axis, which is this, parallel to principal axis, and then it goes to cut F. But where is F? We don't know, right? However, when you draw the first light ray, it will already tell me where this light ray will touch the screen. Therefore, the second light ray must also bend towards so that it will converge at the same place. And where it cuts the principal axis will then be the focal point. Okay, so once you have completed this, you will be able to find the focal length, which is the distance between the focal point and the optical center, and you can also measure the height of the image. Okay, so depending on how you drew it, okay, the size of your pencil tip, okay, this answer may vary by a little. Now, describe the image form on the screen if the object is tilted. That means if the object is tilted like that. Okay, so the answer is the image will be blurred as the light ray will not converge on a single point on the screen. Okay, if we keep the screen at the same distance. Okay, question 3. It shows light rays from a distant object. So distant object means the light rays, the object cannot be seen. Okay, cannot be seen. That means it's too far away. It's larger than the 2f distance. Okay, and it cannot be seen. So the characteristics of this is that the light rays are parallel. Light rays are parallel. Okay, And it says it shows light rays from a distant subject brought to a focus by converging lens on a screen S. So this screen S is on the other side. So object is over here, right? So if something can be captured on a screen, that means it must be real, okay? And must also be, the image must be real and inverted and real, right? So the screen is given to us just like question 2. So we have one light ray, that this first light ray, okay? But we don't know how this light ray will bend, right? The red color one is the answer, okay? So this is the first light ray given to us. We also have another light ray, and again, after passing through the lens, we do not know how it will bend, okay? So in order to help us find where the image will be or where the light rays will converge, we will need this third light ray that you have to draw it yourself, that passes through the optical center. So if it passes through optical center, right, without bending, this is a light ray that I like, okay, it will converge at this point. It will touch the screen at this point. So now we know this is where the image will be if we are talking about the tip of the arrow, okay? Therefore, we can then draw this first light ray, right, after it has passes through the lens to actually meet over here. The second light ray, after it has passes through the lens, we know now how it will bend. Before that, we will not know. So we actually use ray number 3, which is the one that passes through the center of the lens without bending. And if we know where the screen is, we will know where the image is. Okay, then how do we know where is the focal point? So we can actually work backwards. We draw a light ray that is parallel to the principal axis, and it must then also be parallel to all the other light rays. So this is our ray number 4. So I repeat, ray number 4 is drawn by tracing back the light ray that is parallel to the principal axis, which is this part. And before that, it actually came from, it actually looked like the 1, 2, 3, 4 light rays, 1, 2, 3 light rays, and they must all be parallel to one another. Okay, so this is how we can determine the focal point. So actually the concept is very simple. You need to know how to draw the 3 light rays, the standard 3 light rays, which is passes through optical center without bending, parallel to principal axis, then maybe cut F, or cut F, then becomes parallel to principal axis. So you need to know these 3. But of course, the sequence that you have to draw it may not always be the same. We may not always give you the object and lens and focal point and ask you to find where the image is. So it depends on how the question is being structured. So how does the figure show that the object is a long way? The light rays are parallel. So this is very important. So example is a very far away building, or let's say we can even use the sun. So after we have completed the ray diagram, we determine the height of the image. You can actually measure. You measure this height. It's about 1.3 to 1.4 cm. And part C, I hope you all understand how I drew ray number 4. Ray number 4 to work backwards to find where's the find the focal point. Okay. So suggest one instrument which uses a lens in this way, objective lens of a telescope. So refer to the 6 scenarios, 6 cases, okay, in your notes. Okay, question 4. The diagram shows a converging lens used in an overhead projector to form an image of the object. So this was given, the object is here, the image is here. Okay, so we find that the image is actually inverted and real. Why? Because it's actually on the opposite side of the lens from the object. So this is the image. Okay, so in this case, we give you lens. They want us to draw the 2 rays from the tip of object O to locate its image. Okay, so from the tip of object, sorry, actually this image wasn't given. Okay, let me redo this. In the original question, they only give us object. They give us this light ray, number 1. Okay, the green color light rays and the red color light rays and this image wasn't given. Okay, but they did give us a focal point. They give us this focal point. Okay, so this ray number 1 actually doesn't serve any purpose because we do not know how it bends. It's not one of the 3 helpful light rays that we can predict where the image is. So let us draw the first light ray. Sorry. Another light ray, we call it light ray 2 because light ray 1 is already given, but we don't know how it bends. Let's draw light ray 2, which is the one that passes through optical center without bending. So it will just be drawn like that. This is light ray 2, but we don't know how or where the image is. So we actually need to draw another light ray which is parallel to principal axis, and after it touches the lens, it will go on to cut F. And since focal point is given, we know how this light ray, number 3, will actually bend. Right? So this forms 2 and 3. They converge over here, and this is where my image is. Okay? So this is done. Now complete the path of ray XY. So now that we know where the image is, then we can produce this light ray number 1, which is in green color, to come and meet together over here. Okay, so this one is quite simple. The image produced is a real image. Explain what is meant by a real image. You cannot say that, oh, the image is opposite from the where the object is. You must say that a real image is an image that can be formed on the screen. So a virtual image is an image that cannot be formed on screen. Simple as that. Okay, now question 5. You are actually given object and image. Okay, so all these answers in red are not given. So you have object and image, and you find that the image is inverted, right? And it is drawn with real lines, so it is inverted and real. That means the lens must be somewhere in between. Now that you know where the lenses are, because I'm now showing you the answer. So draw one ray from the object to the image to locate the position of the lens. So again, if you know the 3 light rays, you will have drawn this one, ray number 1, which is linking the object to the image using a straight line without bending. So this must be the optical center, and if this is the optical center, the position, then this will be the lens. Okay, now draw another ray to locate the principal focus and label it F. So again, we make use of the 3 light rays, which is the one that is parallel to the principal axis, and once it touches the lens, then it will cut F to meet at where the image is. So there you have it. We have our focal point. Now part C is a very popular question. If the top half of the lens is covered by a piece of black opaque paper, describe the changes to the image formed on the screen. So a lot of you actually wrote that the image will be half. That means like if it's a man, then you can only see half of the man. If the object is a man, you can only see half the image. But which is not true, because let's say if I were to block off the bottom part, I will still have the top part of the lens allowing light to pass through, allowing light to be converging at this point, right? But if I block off the bottom half with a black paper, light rays that's supposed to go below will not be able to pass through. So the image will actually become dimmer or less bright. Okay, question 6, some of you don't know how to answer. Okay, what are you actually given in the question? You were given ray number 1, 2, 3, and 4. Okay, the red color line and the green color line are not in your are not shown. These are the answers. So you find that ray 1, 2, 3, 4, they are actually parallel to one another. If they are parallel to one another, that means the object is very far. Okay, it is not even seen on the screen or on the paper. So indeed, these light rays come from the sun. Okay, and here they tell us F is the focal point. So this is actually the first case whereby the object is very far, and if the object is very far, the image will be definitely at focal plane. But where is focal plane? Focal plane is actually a flat surface, and where's the position? It will be at the focal point. Okay, so the flat surface, let's say if I have a flat surface here, I put a screen here. Okay, at the focal point, it will be known as the focal plane. Plane is actually just a flat surface. Okay. Okay, now in this case, they didn't give us the optical center, but because we know that the lens, the optical center, will be half of the lens, right? We take it that the convex lens is shaped like that. So the optical center, you can actually measure this distance, and then you can get your optical center. And the principal axis, which is this green line here, will then be perpendicular to the lens and passing through the optical center. Okay, let me repeat this. Okay, we need to find the optical center, and hence we need to find optical center first, then we can find our principal axis, because this we are only given lens. Okay, and the lens is, example, if this is 10 cm, so I measure here will be 5 cm, I measure here will be 5 cm, example, right? And this will then be my optical center. Okay, optical center. And I know that principal axis, it must be perpendicular to the lens. Principal axis is perpendicular to a lens, and it is passing through optical center. Passing through optical center. So I draw this green line, which is passing through optical center and perpendicular to the lens. So I put a 90 degrees here. Okay, and we find that ray 1, 2, 3, 4, none of it actually passes through the optical center. So I need to draw my favorite light ray, which is the one that passes through the optical center, which is this ray number 5, which is the red color one. And it must pass through optical center and goes through without bending. And if it goes through without bending, and since my focal point is given, I know where is my focal plane. I know that the image will be here. The image of the sun will be here. Okay, so yeah, you can rewind the video to run through the steps again. Okay, firstly, you need to know that you are given focal point, and you will have this flat surface at the focal point called the focal plane. So this is where all the light rays from a distance object will converge. But in this question, we are not given optical center, we are not given principal axis, so we need to find them first. Okay, it was described earlier on how to find it. So now that we know our optical center, we know our focal plane, we draw ray number 5 to pass through optical center, and where it cuts the optical where it cuts the focal plane will be where all the light rays, how they will converge. So let me just fill in for number 4. Okay, number 2 will also come in here. Number 1 will also come in here. Okay, so they will converge at this point X here. So which part of the EM spectrum has been used to start the fire? Infrared radiation. Okay. Okay, question 7. Question 7, what were you given initially? Okay, you were just given the lens, and you were given the object. Okay, now you need to read the question. A few of you actually asked me how to do this. In the diagram above, when an object is placed before the converging lens, a virtual image, this is important. Virtual means it must be upright and virtual. Okay, upright and virtual, and more importantly, it must be on the same side as object. Okay, now a few of you actually drew your image this way. Okay, when you drew your image this way, it looks like inverted and real. So this is not what the question wants. Okay, so let's continue. The virtual image is formed 5 cm from the lens, so you need to measure 5 cm from the lens. So on the diagram, draw rays to determine the focal length of the lens. Label the focal point. Okay, so now that we know where the image is, but we do not know the height. We only know the image is 5 cm from the lens, and you need to draw it in to scale. Yeah, you need to draw it to scale. Okay, over here the question says 5 cm not measured to scale because this is the answer given by the teacher. So you actually have to measure physically 5 cm. Okay, so we know that the image is here, but we do not know how high the image is, or how magnified, or how large, or how tall the image is. So again, we have to make use of the 3 light rays. So the first one that I like to draw is the one that passes through optical center without bending. Okay, so it goes this way. And then the second one that I like to draw is parallel to principal axis, number 2. But the question is, I do not know where is my focal point. It was not given, right? It was not given. Okay, so that means after the light ray, which is parallel to principal axis, ray number 2, parallel to principal axis, I will not know how it will bend from here. Okay, so I have to go back to ray number 1, and then I draw it backwards because all these are virtual, right? And do you remember at this position where the image is, I draw a dotted line, and where they cut is where the image is. So with this, I can actually find the height of the image. And then with this, I can then draw my ray number 2's dotted line to this position, and I just continue drawing with a straight line, and this is where I get my focal point. So this is quite a difficult question because it's actually the same concept, but it's just that the sequence it's not a very simple sequence. Okay, so you may want to try this again. Okay, so once I know my focal point, I can actually measure the focal length, which is the distance from the optical center to the focal point, and describe the image form. It must be virtual, upright, and lastly the size, which is magnified. Now the diameter of a converging lens is 4.5 cm, and its focal length is 10 cm. An object of height 8 cm is placed 16 cm from the lens. So it seems like there's a lot of information. So maybe I can just do a quick sketch. So this is the diameter. That means this is diameter. That means the whole lens is 4.5 cm, right? Diameter. And the focal length is 10 cm. So this is my focal point. This part is 10 cm. An object of height 8 cm is placed 16 cm. So I have my 10 cm, and if I do a rough sketch, I will have my 2f over here. Okay, so this is another 10 cm, right? And my object is actually placed 16 cm from the lens, so somewhere here. So this is my object example. Okay, my object, and it is of height 8 cm. So describe the image form. So if you know the 6 cases very well, you know that if the object is in between f and 2f, okay, the image will be on the opposite side. It will be inverted and real. Okay, inverted and real. So with this, you can actually already solve for the first two, which is inverted and real. And the size wise, you actually maybe you can just draw. Okay, you draw, and then you can find to see whether is it magnified or diminished. Some students, they actually can memorize the size, but for me, I think I can just quickly get the size by doing my drawing very quickly. Okay, so that's all for this tutorial.